We saw last time that a continuous function defined on a closed interval always has an absolute maximum and an absolute minimum. And it turns out that the absolute maximum always either occurs at either one of the endpoints, A or B, or it occurs at a local maximum somewhere in the middle. And the same thing happens for a local minimum. So how do we find the location of the local maxima and minima of a function? Well, let's imagine you have a function and you have one of these peaks. So kind of a natural peak of a continuous function, more or less, either it's going to look something like that, or maybe it might be sort of a sharp point, right? Sort of a sharp point like that, or a cusp of some sort. So these are all what local maxes look like of continuous functions. In the first case, the tangent line at that point is horizontal, and f prime is 0. And actually, in both of the other two cases, there actually isn't a tangent line. In both of these cases, f prime is undefined. And maybe to further convince you that one of these things has to be true if you're looking at a local maximum, suppose for a second that you had a function where f prime, let's say f prime of a is 2. Well, what that means is that if you zoom in at that point, then after a while the graph starts to look like a line with a slope of 2. But clearly then at this scale you can see that this is not a local maximum or a local minimum. Right? It is not the highest point or the lowest point around, because if I move in one direction I go a little bit lower, and if I go in another then I get a little bit higher. And there was nothing really special about 2 here. If I had any positive number, well then the graph looks more or less like this when I zoom in. And if it's any negative number, well then it will just look like this, and then the same argument basically applies. Okay, so as a result of all of this, we've learned the following, and this is known as Fermat's theorem. You should be a little bit careful though, because there are lots of things that are Fermat's theorem. There's Fermat's little theorem, Fermat's last theorem. But in calculus, Fermat's theorem refers to the following, that if f has a local maximum or minimum at x equals c, well then either f prime of c is 0 or f prime of c is undefined. Now we should be careful about what this says. So it says if f has a local maximum, then the derivative is 0 or undefined. Notice that it is possible for f prime to be equal to 0 or undefined. Maybe I should be a little bit careful here, f prime of a to be 0 or undefined. But for f to not have a local maximum or minimum at a. For example, if you look at the graph of y equals x cubed, well, the derivative of that y prime is 3x squared, and y prime of 0 is, in fact, 0. But now the graph of y equals x cubed looks something like this. So that point right there in the middle, that's where f prime is equal to 0, but that's not a local maximum or a local minimum. So having a derivative of 0 does not guarantee that you're a maximum or minimum. It's just kind of the first test that you have to pass to be a local maximum or a local minimum. And it's going to be a filter that's going to let you, for many functions, throw away a lot of points and usually be left with only a short list of points that could be the maximum or the minimum. So because of that, we make the following definition. We say that x equals c is a critical point of f. First of all, if x is in the domain of f, c is in the domain of f, and if f prime of c is 0 or undefined. Okay, so the critical points are exactly the places that you could have a local maximum or minimum. So maybe let's do a quick example. Let's find the critical points of the function f of x is equal to x squared plus 7x minus 3. So what we're going to do is take the derivative, which in this case is 2x plus 7. And we want to find inputs that make the derivative either 0 or undefined. And well, 2x plus 7 is defined everywhere. So let's just set it equal to 0 and solve. And in this case, you get that x is negative 7/2. So in this case, there is just a single critical point of this function. And of course, this function, x squared plus 7x minus 3, this is just a shifted parabola. And it has its vertex here at this x value of negative 7/2. So that's going to be the local minimum of that parabola. But for more complicated functions, setting the derivative equal to 0 and solving will be a little bit more complicated. Okay, next time we'll start putting all the pieces together and we'll see an example of how to find the absolute maximum and minimum of a function.